Hello, everyone. Hop là. So yeah, my name is Alexis Comar. I'm the CEO and founder of HIPHEN, and I'll present to you today what we're doing on phenomic predictions, more into a research or prospective work in order to help breeding companies. So first, little slide, trying to synthesize a little bit what is the difference between, let's say, classical trait phenotyping and phenomic prediction. Is just that we don't learn on the data the same way. In one case, you try to do similarity matrices, so you have a training data set from another origin, which is phenomic prediction. On the other case, trait phenotyping is just about making sure that your signal is being interpreted in something that is both physical and that can be clearly measured and ground truthed. In one case, it's traditional stuff, and the other one, it's a more, I call it breeder-oriented approach because it allowed me to speak much more with breeders than with crop physiologists before. This notion of phenomic selection or phenomic prediction, we find it back in 2018, and basically it's about trying to predict predicted values, so what they call PVs, full true values, and it was this publication there. What is really interesting there is that they used only NIRS in the publication, so near infrared, and that's, let's say, very small and limited amount of information you can have from sensors when you think of phenotyping. When you think about plant phenotyping, there's 6 dimensions. There's a data point, there's an image, there's a 3D image, there's a 3D image within the radiometric spectrum, so from ultraviolet to radar wavebands going through thermal and visible, etc. And there's time. You can think on time as fluorescence, where your signal is going to be different depending on how you stimulate the plant just before. So the plant can really have different signals in these things. And you can measure all these types of signals through sensors that can be used to do phenomic predictions on top of just the wavebands that was used initially in phenomic prediction. So it's really that I want to enhance in this slide, is to say that there's many ways to measure much more than NIRS to make phenomic predictions. And actually, when you read bibliography, you find a lot of people that try to do things like that. You can find, and there's 2 types of approach. The first approach is to take the signal raw in different ways, such as vegetation indices or time series, and to try to interpret it. Or you can use, as Lucas presented to us, latent space, and latent space whether in time series or not. And that's what we're going to see in the following slides. To illustrate phenomic predictions as we're working it in HIPHEN, I want to use 3 concrete use cases, so it will speak to you all a little bit better, and then we'll try to take the learnings out of it. The first use case will be to try to estimate seed humidity in sunflower heads, and we did that within Helix project. So it's a European project with all the sunflowers breeders operating in Europe. The other one will be yield estimation of hybrids based on the parents that we did with INRAE Le Moulon. And finally, and that's really rare, so we're happy to present it, the way we are helping a very small breeding company advancing their lines in strawberry. So first, the sunflower use case. So once again, European project, the idea there is to be able to estimate every single sunflower head on their trails, which is very big trails, the seed humidity, to be able to know where we are, which one they should harvest, how, etc. To do that, well, it's a whole pipeline that we developed in HIPHEN and that we're operating worldwide already in many things. It's about making the orthomosaic, extracting the plot image, within the plot image detecting all the sunflower heads, extracting all the sunflower heads in order to be able to retrieve what we call the latent space. So the latent space is just using what they call an autoencoders within machine learning and deep learning algorithm. In this case, we use transformers, so the same type of technology as ChatGPT. And there you can see 2 examples of sunflower heads that are, those ones are very similar, and you can see that you have what they call cosine similarity that is very similar. Those ones are 2 sunflower heads that are very different, and they have a similarity that is way lower. And what we've seen is we trained a model based on Toulouse data that we collected in 2023. Of course, when you train, so the training model is 80% and 20% for the prediction in 2023. Of course, it works well. What a surprise. But what is more interesting is that it also works well as prediction in 2024. So using the dataset of 2023, you can predict all the sunflower heads within your trails humidity with relatively good accuracy and a very low RMSE. Those data are going to be done also in Spain and Romania. We're ongoing in the analysis because what they didn't told us, and that complexify a little bit the analysis, is normally you have one sunflower head per plant, and when you start to make crosses and hybrids in a little bit wild fashion with wild genotypes, you can have many sunflower heads, which makes all the pipeline a little bit more complex. So today we're still trying to figure out how to validate the data with this complexity. On the corn, it's where I'm the less comfortable, but basically we have two types of population, a flint population lines and a den population line, and the idea is to see how can we predict the most some breeding values, so some values, some predicted value, which is yield and dry matter content mainly, either through NIRS, either through phenoscale, so through drones, using either traits or a latent space. And basically, we did 6 flights on a trail near Paris, in Le Moulin, where we were able to extract each single microplot, and we're starting to extract each single plant outside of those drone data. And we have more or less 30 traits per date and an image of each plant. And what we see in very quick way is when you're doing random cross-validation, so when you're trying to predict randomly out of the two populations, a couple of them, well, you have everything that works quite well, whether it's genomic prediction, NIRS, phenomic prediction, or UAV drone phenomic prediction. But when you're trying to use a dent to predict flint, then it becomes a little bit more tricky and the predictions are not that accurate. And actually drone is working better than NIRS for yield and dry matter content, and also a little bit better than genomic predictions. And what we're going to do next now is going to use those time series, extract the latent space outside of every single plant of those time series, and to try to make the same exercise with the latent space. So that's the other use case, that is corn. Regarding strawberry use case, so there we work with a brewing company. They basically have nurseries where they're planting, they're making crosses. Strawberry is a really weird plant because it's octoploid. Basically, you cross some plants, you put them into a nursery, so into a field, you collect 100 of them out of 10,000, you put them into the greenhouse, and you wait 5 years to see if you want to multiply it vegetatively or not, because it costs very expensive to multiply in a vegetative way. You don't make seeds out of strawberries, you have plants, so it's stolons multiplication. And so the game for the breeder is to walk into those nurseries where they have 10,000 plants and just to pick the best one. And they literally do that without sensors today in this company. And so what we did was we flew with drones. We're able to measure precocity, as one is the appearance of a first flower, biovolume, number of fruits, and size of the flowers, which is highly correlated to the number of the size of the fruits. And in real time, so just after the drone flight, we gave them we have a tool in Cloverfield, so in our tool, which allows you to sort, to filter many traits at the same time. And so basically, we're able to narrow down from here almost 12,000 plants to 255 plants, which are the plants that he collected and bring to his greenhouse to evaluate further. That's what we do with just complex filtering, so just by filtering on those selected traits, the one that has the best compromise of all. But you can also look at your diversity and look to see which are the 200 you want to select based on traits. So there I'm retaking the same traits and a little bit more. I'm trying to make here is a PCA, so per-simple component analysis. I'm looking at what are my main variability axes. So the first axis is early vigor. So you can see here a plant fruit time. So those are dates. So those are 1 week interval. You can see here a plant that is having a very low vigor. Here, a plant that is having a much higher vigor. And on the second axis, basically, it's the capacity to make flowers. So here you can see a plant that is making very little flowers, whereas here they're making a lot. And you can see that the one in blue, red, and white are the points which the breeder selected while walking in the field and selecting them with his knowledge. And in green, you can see the one that we selected for our filters. And of course, we detected some more to be selected. And what we're doing now is the same thing. We're extracting the latent space of this time series of those plants. So here you can see two plants that are very similar, and you can see that the latent space is quite similar. So it's a bigger spectrum, but it looks like that. And here you can see some time series that are very different, where you can see that the latent space is quite dissimilar. And we can put them into then a diversity map. So here it's not a PCA, it's a TSNE. So it's the way in deep learning you try to represent a diversity map. And you can see that we're capturing different types of diversity, but once again, probably the best plants session for their breeding targets are here. And you can see on the differences that you could see here, how they all are positioning themselves at the same time here, here, and here. So that's basically what we did so far, and what we're doing now is we're also helping them phenotype very precisely all their strawberries, with the hope to be able to try to go into the latent space of the strawberry plants to be able to predict things about the strawberry, the shape and the form of the strawberry, as well by having two data sets on the same plants, one about the plant, one about the strawberry fruit, and then to be able to predict one with the other and things like that. So those are things that you start seeing with genomic predictions, papers like GenoDrawing, as things that we're looking at and that are quite promising actually to take decisions faster, because there you can make decisions extremely fast just after a drone flight if you were able to do something that correlates slightly in such a team. So that's basically some use cases that I'm allowed to disclose. Of course, we're working on many other crops lately with the steps of phenomic predictions. And I would like to try to synthesize or formalize it a little bit, how it works in processes. Well, first you need to have some, what I call B-value, phenomic B-value or predicted value. I mean, what are your targeted value? What do you want to estimate? Then we need to find a way to how do you measure this data? Whether by drone, whether by ground vehicles, let's call them phenostations, so like we see for fruits phenotyping, or handheld devices. Then we need to find a processing tech. Do we want to work directly with the traits? Do we want to work in the image with the latent space of an image, as we did for sunflowers? Or do we want to work in the time-lapse latent space, where there's a lot of development that has been done, either to predict your targeted value, either to be able to make the diversity mapping and to try to select things that are looking like crops or cultivars that are having a high market value. And then, of course, you make your decisions. So that's a little bit how we think of it. I hear a lot, and there's a lot of comparison between phenomic predictions and genomic predictions. I hope that with my talk, we've seen that it's completely different. And the only thing that is slightly competitive with both is maybe we're competing for the same budgets within the breeder's line. So there I agree we should make some comparison to know if it's worth spending money on that or on genomic predictions. And that really depends actually on the size of your budget. If it's already too small for genomic predictions, well, maybe doing a little bit of phenomic predictions, it's way cheaper. So within your breeding program, how it is. And of course, it depends at which stage you're working, and there's more and more papers discussing about that. At which stage of your breeding cycle should you use such technologies as phenomic predictions. And of course, for each crop, there are some specificities, whether they're complex or not, and how they reproduce themselves, etc. I'm going back to my slide. So actually, maybe phenomic predictions is a new way to interpret phenotyping that is a little bit more accessible, I think, to breeders, or at least that can allow providers like HIPHEN to discuss more straightforward with breeders, and not just in ways where we're giving some traits and then the breeder says, what do we do with it? Well, you should do modeling. And how do we do modeling? Well, if you're not a big company, it's really hard to to have all the pipeline. We're starting by removing the e-by-ib component, like I showed in strawberries, removing the soil, etc., to be able to give data that gives you very quickly access to decisions during the growing season, and that's, I think, what is really cool. So we're working on that also to look at how we can transfer some lysometric parameters we're estimating with Icarda in Morocco towards phenobile, so to scale such types of parameters. We're looking with CropXL also on how to use those types of technology in cross-fields estimations. And finally, in just one slide, who's HIPHEN? So HIPHEN is a company that is doing high-throughput phenotyping, and we're trying to give value and to breeders, but also to all the industry, like agro-industries. We try to help people making decisions, and that's why we're really, really onto on-time, low-cost phenotyping. So customers always say it's too expensive. More and more, I have a feeling that we're still relatively cheap. And on time, we're trying to go as fast as we can. And we have really strong targets in the next years to always lower our response time to make sure that people can take decisions during the growing seasons, working with providers such as HIPHEN. So we're a 10 years company, 30 people, subsidiary in US and all that. And please come and talk to me if you want to know more. Thank you.